So, Intekhab, are you okay with being recorded?
I'm okay with being recorded.
Cool. Let's go. Let's hear your talk.
All right. Screen share করি. Sorry, Urmi, you will have to enable screen share. Okay, perfect. আচ্ছা, so because this is a Bangladeshi group, আমি এখানে বাংলা ইংলিশ মিলিয়ে কথা বলবো. This is part of my PhD dissertation research. এই পেপারটা প্রিপ্রিন্ট হিসাবে বেশ কয়েকদিন ছিল, আর তারপর we really worked a lot on trying to get it published. We went through multiple review cycles. It's very close to being published now. It's in kind of the final stages of the process with Genome Biology, which is a journal. So I want to present to you some interesting results about this. So Amar Kachta mainly is in the field of dynamical systems in cancer. So this is computational biology, which I mean, in my opinion, is like the other side of the coin from bioinformatics. They go hand in hand, but there are certain differences. So our work is in computational biology. So at first, I just want to start with why I'm presenting this at BINGS. আমাদের যে collaborationটা এখানে, why I think this is an appropriate thing to talk about. So even though my work is in dynamical systems in cancer, I think dynamical systems and graphs or networks or whatever you want to call it, these two are, again, like two sides of the same coin. They can just say the same story in different ways. And I hope through my talk, you will kind of, if you already knew that, then you will agree with me. If not, I hope I can change your mind about this. The fact that dynamical systems are graphs হচ্ছে একই জিনিস. The other reason I think it's appropriate for our collaboration here is that some of the key outputs by inferences, আমার যে টুলগুলো বানিয়েছি, ওগুলোর some of the key outputs are gene regulatory networks. So I'll tell you what those are if you're not familiar with them. But those are some of the key outputs. Lastly, how I hope that this will be useful or interesting for you. I really think that there's like two big things. একটা হচ্ছে যে my hope is at the end you get a big picture of some of the interesting problems surrounding networks in cancer biology or dynamical systems in cancer biology. That's the first thing. So it gives us some common language to talk about going into the future in talking about these problems. And the second one is I think there are some key innovative parts of my model and evaluation strategy which I think can easily be leveraged by other researchers in very different fields, but I think these parts are easily transferable. So this would be like the transferable skills of my model, which I think অন্যরা ব্যবহার করতে পারবে, right? So throughout this thing, I have no attachment to trying to finish all my slides, so that's okay. Please feel free to interrupt me as much as you want. This is a very friendly, informal conversation. So please, আমাকে just unmute yourself and just start talking, and I'll pause and I'll take your question. All right. So the big picture is that we are interested in gene expression dynamics. So specifically how genes, which are the nodes in my network, how they interact. So these interactions are my edge weights and how they interact with each other to modulate their expression levels. So the expression levels are the values of the nodes, right? So I hope you're already picturing this as a network. This is what's the picture you have in your mind right now is a gene regulatory network. It's basically how genes interact with each other, and এই জিনগুলোর এই ইন্টারাকশনগুলো স্ট্রেংথগুলো হচ্ছে এজ ওয়েট, আর এই জিনের এক্সপ্রেশন ভ্যালুগুলো হচ্ছে নোডের ভ্যালুগুলো, ওকে? And we want to know, in my particular question, I want to know নোডের ভ্যালুগুলো কিভাবে over time change হচ্ছে, right? How these expression values or these node values are changing over time. Now, to be a bit formal, here's the formal problem. I have n different genes. So মানুষের মধ্যে there is about 25,000 gene, yeast has about 6,000. So n different genes, and I have this tabular data where the gene expression of each gene or the expression value of each gene is collected at many different time points. So here's what my table of data looks like for one sample or one person. So তোমার পুরা জিনোমের এই মানুষটার across many different time points, I have gene expression values. And my end goal, this is my input to my problem. এরকম অনেকগুলা sample আছে. Those are going to be the input to my problem. The end goal is I want to estimate some kind of a vector field or a set of ODEs or ordinary differential equations such that I get আমার যেহেতু n different genes, I want an n-dimensional vector field, or in other words, I want n different differential equations, যেখানে কিনা প্রত্যেকটা differential equation of each gene is a function of all the other genes. All right, that's the idea. That's my end goal. Let me pause here and see if this makes sense.
আমার একটা কোয়েশ্চেন ছিল।
হ্যাঁ, মিশুক ভাই বলেন।
আহ, প্রত্যেকটা জিনের যে এক্সপ্রেশনের ভ্যালু গুলো সেটার ডিস্ট্রিবিউশন কি জিন টু জিন ভ্যারি করে, নাকি প্রত্যেকটা সকল জিনের জন্যই এক্সপ্রেশন ভ্যালু একইভাবে ডিস্ট্রিবিউটেড হয় একই রেঞ্জের মধ্যে?
No, good question. It can be very different. So এরকম অনেক it can be very different. কিছু কিছু জিনের যেমন এক্সপ্রেশন ভ্যালু একদম ভ্যারি করে না, more or less steady থাকে, they don't change, whereas other genes will show a lot of variation. So they don't come from the same distribution. And some tools in the field, ওদের কাজ হচ্ছে আপনি যে ভ্যারিয়েবিলিটির কথা বলছেন, exactly ওই ভ্যারিয়েবিলিটিটা ক্যারেক্টারাইজ করা, the heterogeneity in gene expression. But
তো এগুলো নর্মালাইজ করা হয় না বা?
এগুলো আপনি নরমালাইজ করতে পারেন, ডেটা সেটে নরমালাইজ করে, বাট আই থিংক আই ওয়াজ টু অ্যান্সার ইউর কোয়েশ্চেন, এগুলির আন্ডারলাইং ডিস্ট্রিবিউশন সেম না। আপনি নরমালাইজ করে এগুলোকে 0 1 যে এখানে আনতে চান করতে পারেন, কিন্তু আন্ডারলাইং ডিস্ট্রিবিউশনস আর নট দ্য সেম ফর অ্যাক্রস জিনস। এনি আদার কোয়েশ্চেনস?
জিন এক্সপ্রেশন ভ্যালুগুলো কি বাল্ক ডেটা সেটের উপর নাকি সিঙ্গেল সেল জিন এক্সপ্রেশন?
Yeah, great question. So we don't make any assumptions about that. You'll see in my data examples that it is agnostic to the kind of data. এটা single cell থেকে হতে পারে এবং bulk gene expression হতে পারে. So this is agnostic to data modality.
আর ডিফারেন্ট টাইম পয়েন্ট বলতে আসলে কি বোঝাচ্ছেন? একটা স্যাম্পল থেকে তো সিঙ্গেল সেল এক্সপ্রেশন পরে তো এটা মানে
Great
নষ্ট
question.
হয়ে গেল।
হ্যাঁ,
Then
great question.
মানে এটা কিভাবে আসে?
Yeah, exactly. So bulk, let's say if we talk about, so just to give a bit more context to everyone here, single cell হচ্ছে একটা পদ্ধতি যেটা দিয়ে আমরা জিন এক্সপ্রেশন মেজার করতে পারি, কিন্তু the catch with single cell is আমি একটা সেল নিলাম, এটার জিন এক্সপ্রেশন মেজার করতে গিয়ে সেলটা ধ্বংস হয়ে যায়, which means আমি যদি একটা টাইম পয়েন্ট এটার সেল এক্সপ্রেশনটা মেজার করি, তাহলে আমি নেক্সট টাইম পয়েন্টে it doesn't exist anymore. So Tasina's question is a good question. How do I actually get time course data from single cell? So there are a few ways to do it. One of them, the most popular one, is that I'll collect cells at different times. So these will be different cells, but you can arrange them in time based on what's called pseudo time. Right? So single cell use kore pseudo time e gene expression value guloke arrange korte parbo. Right? So you can impute a time even when a time metric does not exist. Right? That's the idea. All right. Great question. Great question. All right. So what is the utility of something like this? It amra keno interesting eta study kora. So first of all, it gives me an understanding of the nature of cancer. So if I'm going to apply this to cancer, it sort of gives me, very, very loosely speaking, equations of motion of cancer. And I know there are physicists in the house, so please don't get offended. All right. So this is, I'm talking very loosely speaking, equations of motion of cancer. Why are these equations of motion? Why might they be useful? Because if I know what these differential equations are, I can make predictions over time. I can say that ছোট ছোট যদি ইন্টারভেনশন আমি করি এই জিন এক্সপ্রেশনে, বা কোনো জিন থেরাপি বা কোনো ড্রাগ দিয়ে যদি কোনো না কোনো ছোটখাটো পারটারবেশন বা ইন্টারভেনশন করা হয়, তাহলে ওভার টাইম এই জিন এক্সপ্রেশনগুলো কিভাবে ইভলভ করবে, রাইট? I can make predictions over time in terms of what happens if I make small changes at initial values, right? It becomes an initial value problem. So that's the utility of studying something in this way, in terms of a dynamical system. All right. Now, the architecture for studying this that we start with is called the NeuralODE, or Neural Ordinary Differential Equation. So if you're in the machine learning space, you might be familiar with something with this. It হচ্ছে 2018 সালে NeurIPS it got best paper, and it has like many citations now. এটার উপরে মানুষ অনেক কিছু বানিয়েছে and so on. So this is my base model. This is what I start with, and then we'll modify it. But let me just use this base model to explain to you how it works. Okay. So our input হচ্ছে this gene expression vector across all n genes, my gene expression vector at my first time point. And the ultimate output I want to get is the predicted expression at the next time point, right? If I get the predicted expression at the next time point, I can compare it with the actual observed expression, and I can do some kind of back propagation and train my model, right? The only change here that you'll see is instead of this just being a regular neural network, this is neural network, এখানে একটা ODE solver বা integrator add করা হয়েছে, right? So ODE solver add করার কারণে কি হয়? The thing that happens is that the output of the neural network, instead of being the expression at the next time point, is the derivative of expression at this current time point. It's the slope. You get the derivative of expression, which this ODE solver integrates to give you the next time point, right? এটা কেন করতেছি, এত ঝামেলা করার কি দরকার? The reason is, ultimately this neural network gets trained as something যেখানে তুমি input দিবা তোমার expression value আর output আসবে derivative of expression value. And if I go back, that is exactly what we want, right? We want these functions f, where if I input the gene expression values, the outputs are going to be the derivative of gene expression value, right? And so by making this small change, where I add an ODE solver, you basically have a neural network that by definition discovers the differential equations. All right?
আচ্ছা,
Let
একটা
me pause
কোয়েশ্চেন,
here.
এটার
হ্যাঁ।
সাথে কোনো পার্থক্য আছে যেটাকে বলে ফিজিক্স ইনফর্ম নিউরাল নেটওয়ার্ক পিনস বা
Yeah, I mean, you exactly. এটার সাথে you'll see exactly that there's a very nice parallel to this. এটার সাথে physics informed এর পার্থক্য আছে in the sense that physics informed is you use আপনার physics এর already existing knowledge to help your model. And bear with me, in a couple of slides you'll see there is a nice tie between this and physics informed neural networks. So I'm glad you brought that up. That's
আচ্ছা,
in a few slides you'll see এটার সাথে connection টা কি, right? And I'll tie it back to you, তখন.
আচ্ছা,
So a great question. Okay, so far so good. This is my architecture. ঠিক আছে? এটা করাতে I get something that helps me discover these differential equations. All right. Now, হ্যাঁ তাসিনা বল।
সো ফার তো এখানে জাস্ট ইনপুট জেন এক্সপ্রেশন অ্যাট সার্টেন টাইম পয়েন্ট আর হচ্ছে জেন এক্সপ্রেশন অ্যাট নেক্সট টাইম পয়েন্ট, এই দুইটা ডেটা ছাড়া তো আর কোনো ইনফরমেশন ইউজ করা হয় নাই বায়োলজিক্যালি মিনিংফুল কোনো কিছুতে ডিরেক্ট করা বা কিছু, রাইট?
At this point এখনো হয়নি, না,
Okay.
not at this point. This is also like this is like yeah, this is the starting point. এটা হচ্ছে base model, and then you'll see it in the next slide. You'll see how I changed it and how I did things
Okay.
biologically meaningful. Yeah, great question. All right, so
Intekhab,
হ্যাঁ
probably
হ্যাঁ
একটা
হ্যাঁ
stupid
ভাই, please.
question.
হ্যাঁ, please go ahead.
So neural network তো output দিচ্ছে differential equation.
হুম।
So এটার কি linearity বা non-linearity control করার কোনো প্রয়োজন আছে বা ওটা কি ইম্পর্টেন্ট এখানে?
হ্যাঁ এক্স্যাক্টলি, গুড কোয়েশ্চেন। সো আমার এখানে আমি আমার নিউরাল নেটওয়ার্কের বিভিন্ন অ্যাক্টিভেশন ফাংশন চেঞ্জ করে আই ক্যান কন্ট্রোল দ্য নেচার অফ দ্য ডিফারেন্সিয়াল ইকুয়েশনস দ্যাট আই অবটেইন। সো আমার এখানে দ্যাট ইউল সি ইন দ্য নেক্সট স্লাইড is that I can control the nature of these differential equations, specifically, aspects like linearity and nonlinearity, by controlling the nature of the neural network itself. আমি কিরকম অ্যাক্টিভেশন ফাংশন ইউজ করব, ওটা দিয়ে ডিটারমিন হয় আমার আলটিমেট ডিফারেন্সিয়াল ইকুয়েশন গুলো কতটুকু লিনিয়ার বা নন লিনিয়ার হবে, রাইট?
তাহলে
So-
কি এটা একটা ট্রেড অফ কোশ্চেন, যেখানে আমি লিনিয়ারিটি যত বাড়াবো আমার কস্ট বাড়বে কিন্তু আবার অ্যাকুরেসিও বেশি হবে, নন লিনিয়ারিটি যত বাড়াবো, এরকম এটা কি একটা ট্রেড অফ?
It is a trade-off, not only in terms of you'll see the biggest trade-off is that আপনি যত ননলিনিয়ারিটি বাড়াবেন,
Okay.
you'll probably get a more and more realistic model, but it gets harder and harder to interpret, right? So
Sounds good.
yeah, so we try to bridge these two things, and I'll in slide 4 you'll see how that happens.
Okay. Okay,
Yeah.
thank you.
But no, this folks, great questions so far. I think I'll just try to remember your questions at the next slide. I can connect all of them. So the problem is this, যেটা আমি দেখাচ্ছি, যেটা Tasnina very nicely pointed out, is that this is still quite black box, right? This is still black box because এখানে আমি just input gene expression দিচ্ছি, output gene expression আসতেছে. There is nothing biologically meaningful, or to be a bit more to phrase it differently, there is nothing biologically explainable about this. It's still very black box. And as a matter of fact, if you notice, a back propagation stepটা কিন্তু শুধু neural network এর ভিতরে যাচ্ছে না. It also goes through the ODE solver. And back propagating through an ODE solver is extremely tedious and very আপনার compute intensive task. It is possible. Applied mathematicians have developed methods for us to calculate derivatives through an ODE solver, but it takes up a lot of memory. Therefore, these methods usually end up being not very scalable. As a matter of fact, 10,000 এর বেশি জিন যেতে হলেই things start to fall apart, right? মানে এই মেথড অনেক স্লো হয়ে যায় বা আমার পারফরম্যান্স খারাপ হয়ে যায়. That's why অন্য যে competing toolরা আছে এখানে, other competing tools that use other methods to kind of try to discover these differential equations, they use some kind of a trick. The most common trick যেটা আমার কাছে মনে হয় দুটো আছে। একটা হচ্ছে যে আমি 10,000 জিন মানে বা ফুল হিউম্যান জিনোম 25,000 জিন আমি স্টাডি না করে I'll study a smaller system of only 100-200 জিন, রাইট? আমার কাছে মনে হয় এই 100-200 জিনের মধ্যে ব্রেস্ট ক্যান্সার ডিসক্রাইব করা যায়, আমি 100-200টা স্টাডি করব। অথবা আমার যে 25,000 জিন সেট, এটাকে আমি কোনো প্রিন্সিপাল কম্পোনেন্টস বা কোনো ডিমেনশন রিডাকশন দিয়ে I bring it down to a lower dimensional space, আর আমি ওই lower dimensional space I try to discover differential equations. The problem is that আপনি যদি এরকম dimension reduction করেন, then again you lose the interpretability, right? Because you are discovering differential equations of principal components. You're not discovering the differential equations of the genes themselves. That's the issue. Good. So how do we solve this problem? And I hope I'll just try to remember all your questions to try to tie it here. We solve this thing by we solve this whole idea of scalability and explainability doing two things. প্রথমত হচ্ছে আমরা, if you notice this block here, right? It is the same as before because a blockটা is heavily modified. Our neural network, I still have a very simple neural network of 2 layers. Here's my second layer, here's my first layer. But এই প্রথম লেয়ারটার দুইটা ভাগ আছে। একটা হচ্ছে this block of what I'm calling sums, আরেকটা block হচ্ছে products. So what I have is these two components of the neural network model the combinations of genes on both the additive and multiplicative scales, right? Because দুইটা জিন লজিক্যাল এন্ড ভাবেও কাজ করতে পারে, লজিক্যাল অর ভাবেও কাজ করতে পারে। So therefore, in an order to try to mimic this, we have this neural network block that takes into account both additive as well as multiplicative synergies of gene expression. এই দুটাকে মিলিয়ে I put these two things together. And if you notice, like I have these activation functions here. These are pre-activation functions which induce nonlinearity into the system, which gets to kind of Shihab Bhai's very good question. And I don't pick something crazy, right? I make kind of ReLU বা আপনার মানে any kind of a hyperbolic tangent এসব জিনিস pick করি না। I pick these activation functions because these are reflective of Hill-Langmuir kinetics from biochemistry. This is how a transcription factor can bind to a gene to change its. These equations describe how basically these are biologically meaningful equations. They describe how one gene can bind with another gene's DNA to modify its expression value. They describe how enzymes can bind to ligands. These are biologically motivated activation functions. All right. So that kind of brings in one aspect of the biological flavor. There is a big aspect left. And the other thing is this kind of brings in the nonlinearity aspect of this. All right. Let me pause here before I introduce the next part of this is the first, I would say, innovation that we had. There's a second step that I'm introduced korbo ekhon, but let me pause here, see what you guys think or if you have any questions. All right.
Is the Hill-Langmuir activation function used in other neural networks as well?
Sorry, একবার বলো উর্মি, আপনি কেটে গেছে।
Hill-Langmuir যে activation functionটা এটা কি অন্য কোনো neural network কেও use হয়?
Well, this is an approximation of the Hill-Langmuir function, right? This is very similar to what is called the soft sign activation function. So this will look very similar to soft sign. This is an approximation of what the Hill-Langmuir is. আমি যদি verbatim Hill-Langmuir এখানে বসায় দেই, this will be very hard to train. So you have to find this kind of a compromise of things that represent Hill-Langmuir, but are also trainable. Yeah, but if this looks familiar, it's because this is a slightly modified version of the soft sign activation function. Okay, good. Now, this is one part of my architecture, which is this biologically motivated activation functions. And the next part is apner a Ronju Bhai's question about how this ties to what's called PINs or physics-informed neural networks, right? Here's this part, right? And then I'm going to just go off on a tangent, and I promise you I'm going to tie it back, okay? So imagine, right? আমি তো এই neural network I'm trying to আমি এখানে আমার input দিচ্ছি একটা time value, আমি next time value বোঝার চেষ্টা করতেছি, right? But we also have a lot of pre-existing literature about how gene regulation works in cancer, right? Breast cancer নিয়ে হাজার পেপার আছে, অনেক স্টাডি করা হয় যে what are some important genes or central genes in this network of breast cancer breast cancer gene regulation, right? এটা নিয়ে আমরা already জানি, we already know about this. So is there a way that we can leverage this prior knowledge to give and leverage this prior knowledge to help our model? So instead of starting from the Stone Age and just looking at your data, it uses your data, but also uses something that the user supplies, like some kind of prior domain knowledge, right? And this also gets at Tasnina's point about biological meaningfulness, right? আমি যদি আগে থেকে জিনিসপত্র জানি, is there a way to integrate that? And what I'm going to show you now is a way to try to do that. So আমরা কিছু simulated input বানাবো that looks like the gene expression values, but they're simulated. They don't really matter. You just have random, like Gaussian values, okay? Imagine I have some kind of a user-supplied domain knowledge model. So this is using other literature, using models from biochemistry, using some things that you have from other investigations. I have some way of saying, if this is my input for gene expression, I have some way of giving me an output for the derivative, right? And I'll tell you what these models look like in a second. But imagine you have access to that. তখন what you can do is আচ্ছা আমি আমার একটা simulated value বানাই, if I put it through this model, I get this output, right? I'm calling it ghost input and ghost output. But what you can also do is I can take this input and I can put it through my network. I can put it through this neural network here, the thing that I'm trying to train. And then out comes, sorry, give me just 1 second. Okay, yeah. So and out pops this output, right? আমার model থেকে একটা ghost output আসবে. What I can then do is, what's going on? Yeah, is I can then compare these two and I can minimize the difference between these two as well. I do a two-level optimization, right? আমার model চেষ্টা করবে যে এই prior এর সাথে আমার modeler output reduce করা, while at the same time a prediction accuracy বানানো. In the process, what happens is you explain the evolution of gene expression over time using these Hill-Langmuir-like neural network, while also respecting the constraints of this prior domain knowledge model. Therefore, you do this prediction in a biologically explainable way, right? It's not black box anymore, right? Not only is it motivated from Hill kinetics, it is also, you also start off with what you already know, right? If I have an idea of how gene regulation works in cancer, I can plug that in here and make sure my model respects those constraints. There is a tuning parameter here that you see, there's lambda prior and then 1 minus lambda prior. So your loss function is going to be a convex combination of this loss and this loss, therefore allowing you to tune how much weight you want to give the prior and how much weight you want to give your data. Okay? আমাদের মডেলটার নাম হচ্ছে Phoenix. এটা খুবই একটা tortured abbreviation, but everything in our lab needs to be named after animals. আর আমার এটা যেহেতু explainable, আমার একটা X লাগতো, right? So Fox or Phoenix, these are the two things, and then I have Fox is too short. Okay. All right. So let me pause here to see if you have any questions, comments, and things like that. This is my architecture. All right. And this thing of how you can integrate prior domain knowledge into your model using this kind of thing, this is exactly the idea behind physics-informed neural networks, where if I'm modeling, let's say, a pendulum, but I know the equations of how a pendulum moves, is there a way I can integrate those equations into my machine learning model? That's the idea of a physics-informed neural network. Here you can think of it, I have some basic idea of how a pendulum moves in cancer, right? আর ওইটা আমি কিভাবে integrate করতেছি. So this is exactly ties to Ranju Bhai's point about physics-informed neural networks. Okay. Let me pause here and see if you have any questions.
এটা কাইন্ড অফ ফিলোসফিক্যাল কোয়েশ্চেন হতে পারে, আমি জানি না এটা অ্যান্সার আছে কিনা। সেটা হচ্ছে যে একটা কমন সমস্যা হচ্ছে যে যেটা আমরা প্রায়র নলেজ আছে সেটা আমরা জানি, তো আমরা যদি পুরো নেটওয়ার্কটাকে ফোর্স করি সেটার সাথে অ্যালাইন হতে, তাহলে হচ্ছে যে যেটা হবে, যেটা আমি নতুন করতে যাচ্ছি সেটা হয়তো একটু ডিফিকাল্ট হয়ে যাবে, মানে নতুন কিছু তার লার্ন করা ডিফিকাল্ট হবে।
Great question.
তো এই জন্য এই জন্য একটা ব্যালেন্স রাখতে হয় যে হচ্ছে এটাতে আমি এত ওয়েট দিব, এটাতে অত ওয়েট দিব, যেটা হচ্ছে নিউ, এটা হচ্ছে ওল্ড।
That's right.
এইটা জাজমেন্টের কোনো টেকনিক জানা আছে কিনা তোমার, জানো কিনা?
So honestly, like great question. So আমাদের এখানে যে this is my tuning parameter, and in a way this gets exactly at your question. How much weight, lambda prior equals to 1 means আমি পুরা prior এর ভক্ত, আর lambda prior equals 0 মানে আমি prior বিশ্বাস করি না. Somewhere in between is the perfect prior, right? The way we do it in this model is cross validation, on
আচ্ছা
held out validation data to find what is the right amount of dependence on lambda on the prior, right? We use cross validation.
আচ্ছা
আমরা
আচ্ছা
মডেলটাকে বারবার ফিট করে we find আচ্ছা কখন মানে at a grid of lambda value use করে what is the right lambda value. Now this is
Okay.
I guess in a machine learning context this is a very empirical way to do it. If you're working with biologists and they say, you know, like usually if you're working with doctors, right, they can say, you know, আমি just 10% believe kori prior, right? And then in that situation, someone can also just say 10%. But if you want to discover lambda by itself, you can take this cross-validation approach. Right? Yeah, that's a long-winded way of answering your question, but I'm not.
না না থ্যাংক ইউ
Yeah,
না
yeah.
ভালো স্যার না আমি একটা সিমিলার কাজ করছি সেটার মধ্যে আসলে এই মানে এক্স্যাক্টলি এটা না কিন্তু হচ্ছে যে কিভাবে ক্রস ভ্যালিডেশন ইউজ করে একটা আননোন প্যারামিটার
Unknown
বের
parameter.
করবো মানে
Yeah.
সিমিলার কাজ মানে আমার করতে হচ্ছে আর কি আচ্ছা হ্যাঁ
আমাদের এখানে hopefully if I have the time I'll show you some results about this prior as
Okay.
well যে priorটা যদি ভুল হয় তাহলে মডেলটা কতটুকু ভুল হয়, right? How dependent are you on the prior, right? You don't want to be what's called a slave to the prior, right? So
yeah
how can we get that? Okay, so let me do that. So one question is এই user supplied prior domain knowledge model গুলা কি, right? এটার উপরে তো আমার মডেলটা অনেক নির্ভরশীল। জিনিসটা কি আসলে? How do I get this domain knowledge model? So this is where these graph priors come in, right? And I also think this part is usually, it's very leverageable if you're working with graph neural networks. So you follow like a Ural Leskovic, Marinka Zetnik, follow karen. They use this kind of ideas a lot. So like I said, I want some kind of a prior domain knowledge model that takes me, if I give gene expression, it outputs, the output is going to be the prior estimate for derivative. So here's how you can get a very easy, basic, almost stupid way of getting it, right? So we have some prior knowledge of how genes are being, how genes that are being modeled might interact with each other. Right? So maybe you have some experimental data, you have some data from sequencing, so on and so forth. Let's say we model এটাকে আমরা একটা নেটওয়ার্ক হিসেবে মডেল করলাম, নেটওয়ার্কের নাম দিচ্ছি n. এই নেটওয়ার্কের adjacency matrix a sub n, I'm going to take that adjacency matrix, right? এই adjacency matrix-এ আমার যদি নেটওয়ার্কে কোনো known activating বা repressive edge থাকে, যে activating বলতে gene expression বাড়ায়, repressive মানে gene expression কমায়, তাহলে আমি ওই known activating repressive edge গুলোকে +1 আর -1 weight দিব। যেখানে edge নাই, those entries in the adjacency matrix will be 0. আর যেখানে I know that an edge exists but I don't know if it's activating or repressive, we simply assign +1. Okay. This is and then we have a very simple linear approximation as a prior model, where if you give me gamma, which is my input, right, input gene expression, my prediction for the derivative or the prior prediction is just this linear model. It's a very simple linear model. But if you think about it, if I go back here, all that a linear model is doing is saying যে gene expression বা এইসব এই edge এই gene গুলার connection গুলা কোন direction, is it in a positive direction, negative direction, or is there no connection? That's all the information that this super simple model is giving. And what I want to show you in the next few slides is how this makes the model extremely powerful. Just this. And by the way, I just gave you one example of what you can use as a prior model. You can make this as complicated as you want, right? If you have some other model from a different lab, that can be plugged in here. There's no problem, right? So Tasnina, if you work with something like a RNA velocity, যেটাকে বলে, if you're familiar with that, you can have complicated RNA velocity models here, which you can use as prior models, right? It's a very, very flexible setup. Okay. All right. So
জাস্ট একটা কোয়েশ্চেন ছিল, এটা কি সামহাউ যে প্রায়র মডেলটা, ওটার গোল কি এটা যে কোন জিন অ্যাক্টিভেটেড হলে হোয়াট আদার জিনস শুড বি অ্যাক্টিভেটেড অর রিপ্রেসড, মানে যেই ভেক্টরটা আমি মানে কম্পিউট করার চেষ্টা করছি সেই ভেক্টরের ডিফারেন্ট পজিশনে যেই জিনের এক্সপ্রেশন আছে সেই জিন তারা তো আবার রেগুলেটেড বাই ওয়ান অ্যানাদার।
that's exactly right. That's exactly
এনি
right.
মডেল দ্যাট ডাজ দিস, যে প্রোটিন ইন্টারঅ্যাকশন সামহাউ প্রেডিক্ট করতে পারে,
Yeah.
কেউ এক্সপ্রেসড হলে আরেকজন কার এক্সপ্রেসড হওয়া উচিত, সেটা
Yeah.
এখানে আমরা ইউজ করতে পারবো।
Exactly right. That's exactly right. Any model that does this, you can
Okay.
plug it in here, right? And we wanted to make it that flexible, right? So that anything that any model you want, you plug it in, because the thing that I show in my paper is even if you start with something absolutely stupid like this, right? It still gives you decent results. So anything that you get more and more sophisticated is only going to get better. Okay. So I have maybe like 3 more slides. I want to show you I have a few more slides. I want to show you 3 big results that I got from the paper. And আমার কিভাবে আমি জিনিসটা করছি। So আমি কিছু সিমুলেশন এক্সপেরিমেন্ট ডিজাইন করছি to estimate predictive accuracy. So আমার মডেলটা held out test সেটে কত বেশি predictive, right? So for that, I start with some ground truth gene regulatory networks. So মনে করেন I have a gene regulatory network like this. I have 2 that's 350 genes and 690 genes, but আমি এখানে একটা toy example দেখাচ্ছি. Imagine I have a ground truth gene regulatory network of 3 genes, and these are the interactions. So এই জিন এটাকে অনেক অ্যাক্টিভেট করে, এটাকে অনেক অ্যাক্টিভেট করে, আর এটাকে হালকা রিপ্রেস করে, right? That's what this is saying. If I start with this ground truth network, I can overlay on this ground truth network a set of ground truth differential equations, right? Using these connections and these edge weights. These are my ground truth differential equations. I can use these differential equations to simulate training and testing data, right? That's this thing. And then I train my model, right? So Phoenix Microsoft PowerPoint e kono ei chobi nai dekhe ami hash use korchi. I hope that's okay, right? So I will train this model, and then I do the predictive test set. I test the predictive accuracy. When I do this thing, and I use the same pipeline, training Phoenix jaga, I plug in other competing models that I talked to you about, the results are really encouraging, because what you see is across many different noise levels in both 350 gene network as well as 690 gene network, our Phoenix outperforms many other methods in the field, right? This OOTB hoche out of the box neural ODE. If I just take the model out of the box and just plug it in, here are the results you would get. And we almost universally beat a lot of the other methods that are in the field, right? And that's quite encouraging. But I think a lot more encouraging than this are the results of explainability, which is where all these things about biological meaningfulness and all these things come in, right? And here's how I measure explainability. The good thing about the Phoenix model, this model, is that it's kind of simple. Even though it looks complicated, it's actually mathematically quite simple. And what you can do with simple models is you can use it you can transform the parameters of that model you can transform the trained coefficients or parameters of that model into a prediction of what the gene regulatory network might look like. That's what I get from here, right? So obviously I'm a predictive accuracy paite pari. In the A modular coefficient use kore, I can also get a prediction for the for a gene regulatory network. And I can compare this network to the ground truth network that was used to generate all of this in the first place. And by looking at the alignment of these 2 networks, that gives me an idea of how explainable my model is, right? Let me just make sure you guys agree with me on this philosophically, right? আমার যে গ্রাউন্ড ট্রুথ নেটওয়ার্ক থেকে ডেটাটা যে সিমুলেট হয়েছে, ওই গ্রাউন্ড ট্রুথ নেটওয়ার্ক যদি আমি কোনোভাবে রিক্যাপচার করতে পারি, it means I'm not making black box predictions, right? I'm making predictions that are biologically explainable. They reflect the causal structure of the biology that is generating this data in the first place, right? And so আমি এই কম্পারিজনটা করে that gives me an idea of explainability, right?
Acha, what is the generation step here? So you start with the network, and then
That's it.
what is being generated?
Yeah, so good question. So I start with a network. I can
Mhm.
use the connectivities of this network to come up with some ground truth differential equations, right?
Mhm.
These are also ground truth. This is the generation step, where if I have a set of differential equations, I can give it random initial values and get trajectories, right? I can get random initial value there. I can get I can simulate time series gene expression data.
Okay, and then at the end, are you back propagating to like go back to the original GRN
No.
to obtain this, or?
No, I'm not I'm back propagating and only finding I'm only figuring out the parameters of this neural network. Right? Once I have the
Acha.
parameters of this neural network, that's this duck over here, right?
Hmm.
That's this neural network. A neural
Hmm.
network parameter ব্যবহার করে I can get a prediction for the gene regulatory network.
Okay.
Not only can it predict expression values on a test set, the parameters of the network can be used to obtain an estimate for the gene regulatory network. And then that estimate can be compared back to the ground truth network to get an idea of how explainable this model is.
Makes sense. Okay.
All right. So if I compare a bunch of these models, a lot of like আমার অন্যান্য models যদি আমি compare করি in terms of explainability, this is the picture that arises. So these are all metrics for graph comparison. I have the area under the curve when I compare the two graphs in terms of precision recall. I have your true positive rate, true negative rate. I have some measure of sparsity, and I have how well the out degree distribution গুলো কত বেশি correlated. This blue polygon here is Phoenix. The brown one is an out of the box NeuralODE. And then this red one, I think is interesting, is Phoenix with 0 weight given to the prior. So this is kind of ties to Ronju Bhai's question, right? What if I don't believe in the prior at all? I give 0 weight to the prior. You'll see that in very low noise levels, these things are comparable. But as noise increases, if you don't give any weight to the prior, then you are no longer explainable, whereas Phoenix remains robustly explainable, right? That's the marginal contribution of giving some value to the prior, right? Let me pause here. I know
একটা কোয়েশ্চেন, হ্যাঁ,
হ্যাঁ।
এই নয়েজ লেভেলটা কি এখানে?
So yeah, good question. So noise level হচ্ছে আমি যে gene expression value গুলো বানাচ্ছি এখানে. So my training data, like the gene expression value, I just add Gaussian noise on top of this. বুঝছেন? So so
okay.
instead of having very nice smooth trajectories, they look like.
Okay.
All right.
আর গ্রাফের যে এখানে যে আমরা এরিয়া আন্ডার দ্য কার্ভ দেখতে পাচ্ছি, এটা কি লিংক, কয়টা লিংক আমি কারেক্টলি পাচ্ছি?
That's
মানে
exactly right. হ্যাঁ, কয়টা লিংক আমি correctly পাইছি, কয়টা incorrectly, ওটা থেকে confusion matrix আসে.
ঠিক আছে, ওকে।
And then you can use that to get the AUC. Right? All right. So folks, I know we're at 1:15. I'm happy to continue for 10 more minutes. Totally up to you.
And let's do 10 more minutes.
Yeah,
চাঁদের
it works
সময়
for
আছে।
me.
Okay. All right. Okay, cool. So this is the explainability, right? And then this I would say was one of our strongest results, because we get to prove that we make these, not only do we make accurate predictions about what the gene expression at the next time point will be, but we do so in a way that's anchored in causal biology. We do so in a way that's biologically explainable, right? And if there's anything that I hope you take away from my talk, it's this thing, right? It's the fact that how can we make sure that our models are explainable by using, and for me, the way I did it is I borrowed heavily from the physics-informed neural network literature. I borrowed that into biology. And then in physics, they know exactly what the equations are, but there is no equation of motion for cancer. And so I made a stupid approximation for it, but that already gives me a lot of benefits in terms of explainability. Okay. All right. So
একটা কোশ্চেন ছিল,
হ্যাঁ বলুন।
এই AUC বা ট্রু পজিটিভ এজ যখন বের করা হচ্ছিল, তখন কি এজ গুলোর সাইনও তো কনসিডার করা হচ্ছিল, রাইট? পজিটিভ।
That's right. Yeah, exactly right. Yeah, this should be like edge sign accounting AUC, right? So মনে করে একটা edge যদি +1 but আমি -1 করছি, that's a 0, right? I got that wrong. You have to get the sign correct and the edge correct.
Okay.
Good. Okay. So, all right. So I'm going to skip this slide and I'm going to go here. Okay. Now, আমাদের ডিপার্টমেন্ট হচ্ছে বায়োস্ট্যাটিস্টিক্স ডিপার্টমেন্ট, রাইট? বায়োস্ট্যাটিস্টিক্স ডিপার্টমেন্টে কিছু extremely annoying মানুষ আছে, তার মধ্যে কিছু মানুষ হচ্ছে Bayesian statisticians. I'm not saying all Bayesian statisticians are annoying, and I'm not saying all annoying people are Bayesian statisticians, but the overlap is significant. And so আপনার এখানে one question that they ask is, দেখো তোমার মডেলে তো prior আছে, so নিশ্চয়ই তুমি অনেক prior dependent. So তোমার মানে how do you know that prior how do you know you don't have over dependence on the prior? That's the question. It's a very legit question. That's why I did these additional experiments. What I did here is for each of my systems, 350 and 690, as the noise level is increasing, so as I'm adding this Gaussian noise to the expression values, I also take, if I add 5% noise, I also take my prior and I corrupt it by 5%. So my prior 5% edge আমি shuffle করে দিচ্ছি, 10%, 20% মানে হচ্ছে আমি 10% বা 20% edge in my prior shuffle করে দিচ্ছি. That's why when I compare this prior network to the ground truth network that I'm comparing against, you'll see that as the noise level increases, the prior gets worse and worse at predicting the ground truth network. Okay. However, the Phoenix model, which is trained on the faulty prior, so this Phoenix model is trained on this faulty prior, does a better job at approximating the ground truth than the faulty prior that it was trained using, right? And I hope that makes, and I hope you understand the value in that, right? I mean, even if this is saying, even if my prior is only 90% accurate, the Phoenix model is 96% accurate. You get a boost from the model, even if the prior itself is faulty, right? And that's an important thing to prove for biological data, because biological data, you never have perfect prior information, right? You always have some level of, your prior is always noisy to some extent. So you must show that আপনার মডেলটা can actually improve on the prior. And to tie it back to Ranju Bhai's excellent question earlier, that আমার prior যেরকমই হোক, I can discover new things beyond the prior. I am not just limited to what my prior is saying. বুঝতে পারছি? Let me pause here and see if this set of experiments makes sense.
জাস্ট একটা জিনিস
হ্যাঁ, বলো।
ফিনিক্সে তো হচ্ছে ওই জিন এক্সপ্রেশন যেই ডেটা টাইম পয়েন্ট ডেটা ওইটা এক্সট্রা ইউজ করছে প্রায়র থেকে, আর তো মডেল আর্কিটেকচার তো আছে, রাইট? মানে সো এই ইনফরমেশন ফিনিক্স তো ওর মডেল আর্কিটেকচার দিয়ে এক্সট্রাক্ট করছে হচ্ছে জিন এক্সপ্রেশন যে ডেটা ওকে দেয়া হলো।
রাইট,
ওকে,
রাইট।
আচ্ছা, এখানে একটা মাইনর একটা মনে হয় ভুল ছিল। 0.975 হবে সেকেন্ড রোতে মনে হয় প্রায়র কনস্ট্যান্ট।
পয়েন্ট এইটার কথা বলছেন?
হ্যাঁ,
I see. Oh, this
2.5
yeah, exactly. Yeah. It 975. That's right. Yeah, that's right. Exactly. This should be 975. Good catch. Good catch. Okay. All right. So this is it. At the end, আমি এতক্ষণ অনেক স্কেলেবিলিটি নিয়ে কথা বলছি, যে আমরা পুরো ফুল জিনোম 10,000 এর বেশি স্কেল করতে পারবো, কিন্তু সব বাচ্চাদের এক্সাম্পল দেখাচ্ছি যে 350, 690. So where is the scalability coming in? For that, we applied it to real breast cancer data, right? So here we have microarray expression, which is not single cell, right? So this is bulk microarray expression data from across many genes. So across close to 12,000 genes from breast cancer cells across 186 patients. So a 186 patient deke, I got them to stand, I bolte like the data set I got is they got these 186 patients, and they were able to order these 186 patients in terms of their trajectory in breast cancer. Which people are more advanced, they stand here. Which people are more earlier, they stand here. And so you get this 186 people. Each person provides one sample. So now you can use that to get a trajectory of 186 time points, right? Each patient is like a time point. You get 186 time points of gene expression across a breast cancer trajectory, right? A very interesting data set. Again, আমার এখানে কিছু prior model ব্যবহার হয়েছে, because it's real data, we can actually do sequencing and see আচ্ছা ঠিক আছে কিভাবে, মানে কোন জিনের সাথে কোন জিন কি এফেক্ট করতেছে, to tie it back to Tasnina's question. Ultimately, we need to have an idea of what gene is acting on what other gene. One way to get it is to look at the promoter sequence of different genes, and that's what I used to create that prior model. And I have আমার তো এখানে কোনো ground truth network নাই, so I validated against ChIP-seq data. So if you're not familiar with this, don't worry, but just trust me that there is a way to validate. Now, what I did incrementally is আমি প্রথমে হচ্ছে মাত্র এই ডেটা সেট থেকে 500টা জিন দিয়ে শুরু করছি. I start with the 500 most highly expressed genes, and I slowly scale up to the full data set. And what you see is our AUC, it goes down over time, but it's still quite good. I get something that's extremely explainable without doing any dimension reduction or any subsetting to genes. Like I'm able to get up all the way here without doing any PC, principal components, any of that stuff. I preserve the interpretability, and we're able to scale up. And to our knowledge, this is the first time that this has been done at that extent without doing any kind of a dimension reduction step. All right.
Is there a sense, could we get a sense of the number of edges there may be?
Yeah, so like if you have this something like 11,000 genes, then the true number of edges is somewhere like real life gene regulatory networks are very sparse. So if I have 11,000 genes, you'll only have maybe like 8,000 edges, right? Only bolte 11,000 times 11,000 অনেক বড় একটা number, right? তার মধ্যে only you'll have like maybe 8 to 10,000 actual edges that exist, right? Because real life gene regulatory networks are very sparse, right? All right, so the last thing I want to show you, এই যে স্কেলেবিলিটি করে এখানে আসলাম, এতগুলো জিন মডেল করতেছি একটা ডাইনামিক্যাল সিস্টেমে, এতগুলো জিন, এটার আসলে লাভটা কি? The lab is that this scaling allows the discovery of new candidate genes or pathways for kind of novel discovery in breast cancer. And here's what I mean by that. Imagine I fit this model, right? আমি এই প্রত্যেকটা এই 4টা different model fit করলাম, ছোট মডেল থেকে শুরু করে all the way to a বড় model. And each of these is a dynamical system model showing how every gene affects every other gene's differential equation. I can use that to understand what are the key genes or the most important genes in each of these models, right? কোন জিনকে আমি ছোট একটা চেঞ্জ করলে সবচেয়ে বেশি অঘটনা ঘটে, ফর এক্সাম্পল সবচেয়ে বেশি চেঞ্জ আনে, ডাউনস্ট্রিম চেঞ্জ আনে অন্য জিনের মতো। দিজ আর মাই ড্রাইভার জিনস, আর if you think about it, these are the things that have the highest harmonic centrality in my network, right? So আমি ওই জিনিসটা ক্যালকুলেট করলে I get an idea of what are the most central genes across all these different, all my 4 models. When I start with a very small model and when I scale up to the full data set, okay? And this is sort of considered like this would be on the same order of magnitude as like human genome scale. So what you see is the important genes, some of them, for example, a WT1, it's a known important gene in breast cancer. It remains somewhat important when you scale up, but you discover other things that you don't discover that you don't see in a smaller data set. So in a smaller data set, this EGR4 is not considered because it's not highly expressed. However, when you actually scale up to the full thing, you see that this is actually central to the dynamics of breast cancer. So এটা দেখা আমি কি বোঝানোর চেষ্টা করতেছি যে scaling is not only useful for the purposes of scaling itself. Scaling is useful because when you actually scale up to this full genome size, you discover more things that are biologically meaningful in the context of breast cancer. Lastly, what we can do is আমরা এসব এই gene score গুলা ব্যবহার করে, and I won't get into the details of this, I can convert these gene scores into pathway scores. এই gene গুলা যেগুলি overexpressed বা overrepresented, what does this mean in terms of pathways? কোন pathways গুলো overrepresented by overexpressed? And what you see is a similar picture. When I scale up from ছোট data set all the way to the full size data set, there are a lot of important things that show up that are important in context of cancer. For example, apoptosis or cell death. This estrogen-dependent nuclear event, which is important for hormonally regulated or hormonally controlled breast cancer. There are a few other things like this ESR-mediated signaling, which is estrogen signal receptor-mediated signaling. That thing becomes important, and you discover it as being important when you're able to scale up. So only when you scale up, only when you're able to scale up, which it অন্য model allow করে না, but আমাদের model allow করে, only when you're able to scale up do you discover these important things as being central to the dynamics of breast cancer progression, all right? And therefore central to the network of breast cancer progression, all right? So I think this is a good place for me to stop. Let me pause here, see if you have any comments, questions, and so on. But thank you very much for your patience, and specifically thank you to all of you for the very, very informed questions. It was very obvious that you were able to you were following along, and I really, really appreciate that. Thank you.
আমার আগের স্লাইডে একটা কোয়েশ্চেন ছিল, তার আগে হ্যাঁ এখানে এরিয়া আন্ডার দ্য কার্ভ, এই নাম্বার অফ জিনস 500 জিনস, এটা আমার একটা মডেল ট্রেন করার পরে তারপর ওই মডেলের আউটকাম হিসেবে আমরা লিঙ্ক গুলোর সাথে কম্পেয়ার করে এরিয়া আন্ডার দ্য কার্ভ পাচ্ছি। এখন মডেল ট্রেনিংটা কি আরো কোনোভাবে এপক বাড়ায় বা কোনোভাবে কি AUC-টা কি বাড়ানোর ওয়ে আছে এখানে, নাকি এটাই কাইন্ড অফ ম্যাক্সিমাম AUC পাওয়া যাবে এখানে?
Yeah, this is I mean, এটা হয়তো করা যেতে পারে, right? But that would be cheating, right? I mean, কেন বলতেছি cheating? Because in real life, I don't have access, like, আপনি মানে what you want to do is আপনি একটা model train করবেন, right? You train your model using your prior knowledge, using your actual gene expression data. You figure out what is the best time to stop training your model using some kind of a validation set or some kind of cross validation. Once I have that model, then this is the post hoc thing. At the very end, you calculate this AUC, right?
Okay.
If I train my model
with the validation,
with the validation, আমি যদি validation improve করার জন্য ট্রেন করি তাহলে তো এটা ট্রেনিং হয় না।
হ্যাঁ, আমি হাইপার প্যারামিটার অলরেডি জেনে যাচ্ছি,
right? Exactly. All right.
থ্যাংক ইউ ফর দ্য প্রেজেন্টেশন, অনেক ভালো ছিল।
Oh, thank you. Yeah,
আমি
go ahead.
সায়েন্স গাইডেড মেশিন লার্নিং, ফিজিক্স গাইডেড মেশিন লার্নিং এর আসলে লস ফাংশনের চেঞ্জ, ওই জিনিসটা জাস্ট মাথায় মানে ইমিডিয়েটলি যেটা আসে আর কি, লস ফাংশন আমি অ্যাড করলাম কনস্ট্রেন্ট, বাট আর্কিটেকচারে কিভাবে চেঞ্জ করে আর অ্যাক্টিভেশন ফাংশনে চেঞ্জ করা যায়, এই আইডিয়াটা আসলে এখানে বেশ ভালো ছিল।
Oh,
So it is
thank you.
something new
Yeah.
I have learned here.
Yeah, thank you very much. Yeah. I have a follow, আমার যেটা মানে আরেকটা পেপার যেটা আমি কাজ করেছি, যেটা maybe at some other point present করব, that has to do with the idea of neural network pruning. So এখন একটা অনেক বড় মেশিন লার্নিং কমিউনিটিতে একটা আইডিয়া আসছে কিভাবে নিউরাল নেটওয়ার্ককে প্রুন বা স্পার্সিফাই করতে হয়। ওইখানেও মানে I think my whole philosophy of my PhD was যে আচ্ছা মানে কোনো কিছু করার জন্য you need to include some kind of a domain knowledge, মানে খালি হাতে এসব করা যায় না, right? So it's called the no free lunch theorem. You have to start from something. So ওই pruning strategy গুলো তো we found a way to integrate domain knowledge there. That's another way to kind of put a loss function ছাড়াও, that's another way to integrate domain knowledge. All right. But Tasneem, thanks for the great questions. I think they were very nice.
It was very good. Thank you so much, Intekhab, তোমার পুরো ইয়েটা আমাদের সাথে শেয়ার করার জন্য. And it's already published.
Yeah, it's
almost, right?
It's in the last day, exactly. Amar ekhane, if you scan this, it'll take you to my preprint. It's in the final stages of it's not already published. It's in the final stages.
Final stages, right?
We're getting there. We're getting there. Etake amar I had a very paradoxical experience with this. I took it to different conferences. All the conferences I took it to, we won awards. We won like best poster award, travel fellowship, eta. I presented this to one of the people the person who discovered RNA velocity. He said it's excellent. I presented to this physics informed by scientific machine learning founder, this guy, his name's George Karniadakis, Brown University. I'm Brown নিয়ে এটা present করছিলাম, and he really liked it. সবাই এটাকে ভালো বলতেছে, but এটা rejectable reject খেয়ে যাচ্ছে, death reject. So it was very paradoxical. এক সাইডে মানুষ বাহবা দিচ্ছে, আর এক সাইডে ভাই এডিটরি ক্লিয়ার করতে পারতেছেন। So finally, I think
I'm curious, like do you know what the rejection, মানে কোন এরিয়া গুলোর জন্য ওরা মেইনলি গিয়েছিল?
Yeah, so we sent it to like nature methods. I think one thing might be that we were aiming high, so that's always a reason. But I think also আমার কাছে লাগছে যে ওরা দেখছে NeuralODE, single cell, and at a knee-jerk reaction of also this has been done before, so we're not going to publish it.
Okay.
There's a lot of knee, but without really engaging with it and seeing there's some key যেটা Tasneem point out করলো. This is not a regular neural network, right? We changed it. We changed this part, obviously. And then this part, we got it from a different field. We got it from physics, and we brought it in. We modified it to work, to be amenable to the cancer biology. I don't even think they engaged with it properly, right? And then it was a very knee-jerk no, যে না এটা আমরা নিব না, because এরকম জিনিস হয়তো আগে করা হয়েছে.
Cool.
Alright.
I think our question.
No, I just wanted to say thank you. It was a very good talk. আমি এটা আগেও শুনেছি, বাট আমার কাছে অনেক ভালো লাগে প্রত্যেকবার শুনলে। আর Intekhab, আমি একটু ব্যাকগ্রাউন্ড দিতে পারি, বিকজ আমি জানি Intekhab অনেক 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 কষ্ট করেছে এটার জন্য, and it shows. So really proud of you, and অনেক ভালো হয়েছে।
Oh, thank you very much. Thank you. Yeah.
আর আমাকে যেতে হবে, so it was nice meeting everyone. আমার ক্লাস শুরু হবে, so আমাকে যেতে হবে এখন।
ঠিক আছে, and I think we can also
Probably
wrap.
এর পরের গুলাতেও আসতে যদি পারি তখন পরের গুলাতে আসবো। So hopefully, thank you Urmi for organizing it. So no problem. Okay.
Bye bye.
Bye.
I think we are also at the end of time. I don't want to take too much time of people. যদি সবার তো এখন পরিচয় আছে, you have your email addresses as well. তো কেউ যদি কোনো collaborate করতে চায়, if you have more questions about Intekhab's project, maybe you want to know something on a detailed level, then please feel free to reach out to him.
Yeah, please. Yeah, feel free to reach out. Definitely happy to also learn more about your work, and happy to just connect.
ঠিক আছে, তাহলে I think we're already. হ্যাঁ, কিছু বলবো?
সবার ভালো দিন যাক।
Yeah, exactly. Yeah.
নেক্সট উইকের এজেন্ডাটা কি ছিল?
Next week I don't have a plan yet.
Okay.
I think Khalid is presenting next. Is that true?
Khalid অথবা আমি, and also there's a spring break in the middle, so I have to check with people যে কেউ কি spring break এর জন্য, if there's a schedule change there.
Okay.
But জানিয়ে দেব আমি।
ঠিক আছে।
All right.
ঠিক আছে, হ্যাঁ, thank you.
All right. Thank you.
সবাই,
Thank you.
special thanks to Intekhab.
Bye.
Bye bye.